Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Dr. April Rosala Lehman, who received her PhD just moments ago in January under Dr. Professor Sudan, and it's which laboratory is it? Computer Science and Artificial Intelligence Laboratory, and she has interest in algorithms for networking and routing, scheduling, game theory, and communication. So we'll let her talk about her recent interests. Here, use your microphone.
I think it is, yes. Okay. Great. Well, thank you. It's good to be here. And I definitely want to encourage everybody to stop and ask me questions if there's anything that I either go too quickly by or something just raises an interesting thought for you. Okay, so I'm going to be talking about the capacity of a network. And my name is April Lehman, and this is joint work with Nick Harvey and Robert Kleinberg, who are also at MIT. Okay, so I'm going to start off with something some of you may have seen. It's a pretty basic question. What is the capacity of a network? So here I've drawn a network, and I'm assuming that there's a source with some blue stuff, and it's trying to send that stuff to a corresponding blue sink. And there's also a source with some red stuff that's trying to be sent to the red sink. So the question is, how much blue and red stuff can we send through this network? Now I'm going to assume that each edge in this network has some capacity. In this case, let's say the capacity is 1. So that's going to impose some limits on how much stuff we can send. But what's kind of interesting is that the amount of stuff that can be sent also depends on what it is we're actually trying to send. So for example, let's suppose at first that what we're trying to send is fluid. So suppose this is a network of pipes, and we've got some blue fluid and some red fluid that needs to get between their sources and sinks. So what happens in that case is that that middle edge from C to D acts as a bottleneck. And the fluid from the blue source and the fluid from the red source has to actually share the capacity of that middle edge. So what that means is that I can split this capacity evenly between the two commodities and send half a unit of blue fluid and half a unit of red fluid. And in this sense, we would say that the capacity of this network when I'm sending fluid is a half, because each edge has capacity 1, but I can only send a half unit of flow between each source and its corresponding sink. Okay, but on the other hand, suppose that what I'm trying to send is information. So in particular, let's assume that the blue source has a bit, which I'm calling x here, and the red source has a bit, which I'm calling y. So now what happens is I can do something different. I can send x on both of the outgoing links from the blue source, and I can also send y on both of the outgoing links from the red source. And then the node C has both x and y, and it can compute the exclusive OR of the 2 bits and send that on to D. Right? And then that can get forwarded onto both sinks. Okay, so now this blue sink here, which actually wants to learn x, is not going to learn x directly. What it's going to learn is it's going to learn the value of y, and it's going to learn the exclusive OR of the 2 bits, and it's going to use that to compute the value of the bit it actually wanted to know. So in this case, I'm sending 1 bit on each edge in the network, and I'm getting 1 bit from each source to its sink. So we'd say that the capacity of this network is 1. So what this example is demonstrating is that the question, what is the capacity of the network? Well, for that question, the answer actually depends on what we're assuming we're trying to use the network to do. And in particular, it's showing that information and fluid are not the same thing. This is a little bit strange because we understand fluid flows fairly well. And in fact, it's really natural to want to try and model information flows using fluid flows. But as I've showed you, information can do things that fluid can't. It can be copied, and it can be encoded. And it makes for this kind of strange situation. On the one hand, we use information networks all the time. There's some possibility that there's people sitting in their offices right now watching this talk over an information network. And yet, we don't know that much about the capacity of information networks. In fact, here's a quote from one of the leading textbooks, which says that there is as yet no unified theory of network information flow. But there can be no doubt that a complete theory of communication networks would have wide implications for the theory of communication and computation. So the goal of this talk is to try and move in that direction of understanding the capacity of an information network. And the theme is that I'm going to blend information theoretic techniques with combinatorial ideas to approach that goal. So information theorists have developed a deep understanding of complex communication problems, but over structurally simple networks. And on the other hand, there's been a lot of effort in the combinatorial side to develop an understanding of simple, i.e. fluid flows, through very complex networks. But as we've seen, information is not fluid. It flows in different ways. And so what I want to do is I want to take the best ideas from both of these areas, bring them together, and somehow develop an understanding of the capacity of information networks. OK, so as I said, there's been a lot of work in the past on understanding fluid flows in networks. And I'm going to first review that background. So back in what I consider to be the dawn of time, Ford and Fulkerson proved their max flow min-cut theorem, which says that the amount of fluid that can be sent between a source and a sink is determined by the minimum cut between that source and the corresponding sink. And this has been extended to show that if you have two commodities trying to share a network, then the minimum or sparsest cut in the graph determines the maximum flow. But on the other hand, in 81, Okamura and Seymour presented an example in an undirected network where there's a gap between the sparsity of the network and the amount of flow that can be sent through that network. And more recently, Leighton Rao showed an even larger gap for an expander, where they show that there's actually a log n gap between the sparsity of the graph and the total amount of, the multi-commodity flow that can be sent through that graph. Yes?
So this is presumably for more than two flows, because otherwise it would contradict.
Yeah, so this is for actually n squared commodities. So there's essentially for this example, you have for every pair of nodes, there's an attempt to have a connection between them or a flow between them. Okay, so there's this sort of very deep theory that's gone on and tried to understand how cuts relate to fluid flows. But we're not interested in fluid flows, we're interested in information flows. So let's look at what's been done in information theory. So if I said the dawn of time was 63 or something, well, Shannon, long before the dawn of time, was considering entropy. And in fact, proving some very interesting things about characteristics of information. So Shannon proved that entropy is a submodular, non-negative, and non-decreasing set function. And now I'm going to skip a whole lot of information theory, which, as I said, developed this deep understanding of complicated communication problems, but over more structurally simple networks. In 2000, Allsweet et al. Made the first, what I consider, significant progress on the question of understanding the capacity of an information network. And what they did was they showed that if you have a single node trying to multicast information to a set of sinks, then the amount of information that can be sent from that node to all the sinks is determined by a min-cut condition. So this is kind of interesting because even though we're looking at information flows in this case, there's still a min-cut condition that's determining the capacity of the graph. And in 2003, there was an algorithmic result which showed that you can actually achieve that multicast capacity using a polynomial time algorithm. And also in 2003, Songyung and Said looked at the case of directed acyclic graphs and came up with a general outer bound or upper bound on the rate or capacity of the network. So I'm going to use outer and upper a little interchangeably in this talk. Now, more recently, people have started thinking about undirected networks. And in 2004, Lee and Lee conjectured that the maximum information flow is equal to the maximum multi-commodity flow in information networks. What this is saying is that if you have an undirected network and you're trying to support a bunch of point-to-point connections, maybe all these funky things we can do with information doesn't really help. Maybe all we need to be doing is just multi-commodity flow. In 2005, Kamal Jain and some other people here, as well as ourselves at MIT, verified this Lee-Lee conjecture for what I'm going to call an interesting class of graphs. And I'm going to get to that at the end of the talk. Okay, so as I said, the goal of this talk is to roughly blend combinatorial and information theoretic techniques to understand the capacity of an information network. And I'm going to start by giving a formal model for information flow in general graphs. And then what I'm going to do is I'm going to consider a cut-based condition that's a natural upper bound on the rate of information flow. And what we'll see is that this cut-based condition is actually loose. But the techniques we're going to show, or we're going to develop to prove that looseness of this cut-based condition are what are going to allow us to come up with a tighter upper bound on the capacity of a network. And the basic idea is going to be that we're going to derive some strong information inequalities based on the graph structure, and we'll combine these with some facts about entropy, and what's going to come out is, well, the only outer bound, and therefore best outer bound, known on the capacity of a general network. As a special case, we'll be able to use this outer bound to verify the Lee conjecture for the same class of graphs that Jane et al. Considered. Okay, so this question of a capacity of an information network has been considered within the area of what's known as network coding. So for the network coding problem, I assume that we're given a graph G, which is what I've drawn over here on the left. Each edge in the graph has some capacity. And there are k commodities. For each commodity, there's some set of sources and a set of sinks and a demand between the sources and the sinks. So over here, I have a special case where there are two commodities, and each commodity only has a single source and a single sink. So all the results that I'm going to present today apply to this general setup that I have, where I'm not making any assumptions about whether the graph is directed or undirected and so on. And I'm not making any assumptions about the sources, number of sources and number of sinks. But for the purposes of this talk, I'm going to use a simplified model. So I'm going to assume, just for this talk, that each edge in the graph has capacity 1, and that each commodity has a single source and a single sink, and the demand for each commodity is 1. Yes?
You're assuming that the graph can be either directed or undirected?
Yes.
Except the picture seems to show it is directed. So.
Yeah, well, I wanted to give an example graph rather than just a blob.
Okay.
So yeah, as you said, this graph here is actually directed. And I'm actually going to do one other simplification just for the purposes of analysis, which is that I'm going to assume that for each sink, there's a single in edge, which is a directed edge. And for each source, there's a single out edge. Okay? And that's just going to make things a little bit nicer later on. I'll refer to the single edge in edge to a sink as a sink edge, and the single out edge from a source as a source edge. Okay. So that's the problem we're going to be considering. Now I want to describe what a solution is to the network coding problem. Okay, so we're going to represent a solution as a sequence of rules, essentially a straight line program. And the idea is that each rule is going to specify some information to be transmitted across some edge in the graph. Now we're going to insist that the first set of rules transmit essentially the message for each commodity across its source edge. And then from then on, for each non-source edge, we're going to insist that if a rule states that some function is supposed to be transmitted over the edge uv, then that function had better be computable from the information sent to you in previously stated rules. And then finally, we're going to insist that this sequence of rules ends with a set of rules that say that each sink edge transmits the appropriate message for its commodity. Okay, so let me describe how this relates to what I've drawn over here, which is the solution that I gave you before. So here I've actually drawn the messages that are going to be transmitted across the edges that are going to be transmitted on the edges. And what we would do in terms of writing the sequence of rules is we'd start out by having a rule that specified that the blue message is transmitted across the blue source edge, and the red message is transmitted across the red source edge. Those would be the first two rules. After that, we could define rules that would say that the blue message is transmitted across this edge and this edge, and rules that said that the red message is transmitted across this edge and this edge. Now, at this point, this node here has received both the blue and the red message in previous rules. Therefore, we can have a rule now stating that the exclusive OR of those two messages is sent over this middle edge. And we're going to wrap up by having rules that specify that, say, the red message has to be transmitted over the sync edge for the red commodity. Okay. And I want to, this is maybe not the most intuitive definition of a solution, but I want to point out a couple things about it. First of all, we're going to allow multiple transmissions across each internal edge. So what that means is that if we have a cycle in the graph or something, we can allow edges to be transmitting more than one message. Even for directed acyclic graphs, we're allowing internal edges in the graph to transmit multiple symbols.
What, if any, constraints are there on the functions that you have to put?
So I'm making no constraints on the functions.
So they can have memory, for example, and remember what happened during it.
Exactly. That's what we're hoping, in fact, is that you're allowed to compute any function of anything you've received in previous rules. It's just not allowed to depend on future rules. And in fact, there's another thing which I'm doing, which is that I'm not stating any limits on the amount of information that an edge is allowed to transmit at the moment. Okay, so this might seem a little weird because I went to all the trouble to define capacities for the edges. But I'm not going to use that in terms of defining what a solution is. We're going to use capacities in terms of defining the rate of a solution. Yeah?
Is there any notion of time or delay?
No notion of time or delay. So you can also define this in terms of a delay model. But this is just saying, for a particular node, if it knows what the network coding solution is, it just would need to know that it's collected all the appropriate messages that it needed that appear before the one it wants to transmit.
So previously, in that definition, refers to
The sequence.
of defining these functions.
Yes. Yes. Okay. So as I said, I'm going to use the capacity of the edges to give us a notion of what the rate of a solution is. So let's assume that the messages for each commodity are chosen independently at random. Well, then the straight line program is going to define a sequence of symbols that are transmitted across a given edge, and that sequence is now a random variable. We'll say a solution has rate r if each of the sources is able to transmit at rate at least r, and the edge capacities are not exceeded. What I mean by that is that for a directed graph, I'm going to assume that the entropy of the information transmitted across an edge E is at most the capacity of the edge. And for an undirected graph, I'm going to assume that the sum of the entropies of the information transmitted in both directions across the edge has to be at most the capacity of E. Okay, now I'm using a shorthand here, so entropy of E is referring to the entropy of the information transmitted across that edge. Okay. Yes?
And the rate is defined as symbols per unit time? What is the rate defined? I mean, what are the units of rate?
I guess I'm defining it as a rate. You can think of it as defining it as a ratio of entropy, so it's not really a unit. But I guess I'm saying that the entropy of a source has to be at least some rate, so I guess it would be symbols per unit time. But you can also think of, because I'm partly using entropy in that definition there because I'm allowing you to use skewed distributions for your sources if you want to. Okay. Okay, so that was the formal model for information flow. And now what I'm going to do is I want to consider a natural cut-based outer bound on the capacity of a network. And what we're going to see is that this outer bound isn't tight, but the ideas that we'll use to prove that are what's going to motivate the tighter outer bound that we'll come up with. Okay, so the first guess that everybody has as to an outer bound on capacity is sparsity. And what sparsity is for a cut, we say that the sparsity of a cut is the ratio of the capacity of the edges in the cut to the number of commodities with no remaining source sync path when I remove those edges from the graph. Okay? And the sparsity of a graph is the minimum sparsity over all cuts. So what's kind of funny is that everybody guesses this as an upper bound on capacity for information networks. And this is despite the fact that everybody sees this example as the very first example of how information flows differently than fluid flows. And this example is the example that shows that sparsity is not a valid upper bound for directed graphs. Okay, so but it's important to understand why it's not. So suppose I take this green edge here, and I consider the sparsity of just that edge. So in other words, the capacity of this edge is 1. But if I look at the number of commodities with no remaining source sink path when I remove that edge, it's 2, because there's no path from the blue source to the blue sink, and there's no path from the red source to the red sink. So that says that the sparsity of this graph is a half. But I've already shown you that there's a rate 1 solution. So this says that sparsity is not an appropriate upper bound for information flow. And the reason it's not, if you remember the solution, is that we actually use the fact that we can send some information from the red source to the blue source in order to be able to increase the capacity of the network. So what we want to do is we want to take care of that when we're considering our cut condition. So that motivates the condition which I'm going to call meagerness. So I say a set of commodities P is separated by a cut if there's no remaining path from any source in P to any sink in P. It doesn't have to be for the same commodity when I remove those edges from the graph. Okay? And the meagerness of the graph is going to be the minimum over all sets of commodities P and cuts that separate P of the ratio of the capacity of the edges in the cut to the number of commodities in P. So just to make this definition a little bit clearer, let's look again at this example. Suppose we take our set P to be both the blue and the red commodities. Okay? Then in order to separate them, I'm going to need to cut, let's say, these 3 vertical edges here. Right? So the meagerness of that cut would be 3 halves. Does that make sense? So I need to separate not just the blue source from the blue sink, but also the red source from the blue sink, and the blue source from the red sink. Okay? But on the other hand, the meagerness of this graph is actually 1. Because if I look at this single green edge, it does separate the blue source from the blue sink. So if I let my set P just be the blue commodity, then the green edge separates that set. Okay, so for this example, meagerness actually tells us exactly what the capacity of the graph is, because the meagerness is at most 1, and I've showed you a rate 1 solution. It turns out that, in general, meagerness is not a tight upper bound. And I'm going to need to use this example to show you why. So for this graph, there are 3 commodities now, a green, a red, and a blue commodity. The green commodity has its source in the upper left and its sink in the lower right. The red commodity has its source in the upper right and its sink in the lower left. And the blue commodity is going from the top of the middle, top in the middle down to the bottom of the middle. Again, I'm going to assume that each edge has capacity 1. So I'm not going to run through all the possible sets of commodities and cuts that separate them. But it's not too hard to see that the meagerness is at most 1 of this graph. Again, if I take the single black edge, it separates the blue source from the blue sink. On the other hand, here I've drawn a flow solution that has rate 2/3. Okay, so this is a solution in which from the green source to the green sink, I'm going to send at rate 2/3. From the red source to the red sink, I'm going to send at rate 2/3. And for the blue commodity, I'm going to split the flow along the 2 paths. And this is simply a flow solution. I mean, you can implement this, using bits, but I'm not doing anything clever in this solution. And so the question is, is doing something clever using the fact that we're sending information, is it possible to get somewhere in between the meagerness of the graph, which is 1, and the flow solution?
Sorry, I don't understand why the meagerness of that graph was 1. If you cut that edge that you showed previously,
Yeah. Yes.
you could still go from blue to blue, right?
Yes.
On the side edges.
So when you're computing the meagerness, you do 2 things. First, you choose a set of commodities, which doesn't have to be all commodities. And then you find a cut that separates all the sources from all the sinks. Right? So when I consider this edge, I'm going to choose my set of commodities just to include the green commodity. Okay. Oh, did I?
Yeah.
I'm sorry.
Okay. Yeah.
Yeah, I'm not colorblind, but when I talk, I become colorblind. So at least that's the way I see it. So stop me if I do things like that again. Okay, so now the question is whether or not we can do something when we're sending information rather than just fluid to sneak in between these 2 bounds. And the answer is no. What I'm going to do is I'm going to show you that the maximum rate for this example is actually 2/3. And the way that we're going to get a tighter upper bound on the information flow is we'll use some entropy-based arguments. And these entropy-based arguments imply that meagerness is not a tight bound, but more importantly, they motivate the ideas that we're going to use to create our outer bound on capacity. Okay, so I'm going to need the following notion for this proof. I'm going to say that a set of edges V informationally dominates a set U if the information that's transmitted across the edges in V is sufficient to compute the information that's transmitted on edges in U. Okay? When that happens, a direct consequence of the data processing inequality is that the entropy of the edges in V is equal to the entropy of the edges in U and V. Okay. So let's consider this example for a minute here. I'm going to let my set V be the two black edges, one of which is the source edge for the green commodity, and one of which is the edge F. Then, just looking at the structure of the graph, the information that gets transmitted across this sink edge here, it's got to flow through these two edges. There's no other place that it can come from. Okay, so I'm being a little hand-wavy here, but the idea is just look at the structure of the graph. You see that what's transmitted on this edge has to be a function of what's transmitted on those two edges. Okay, and that tells us that that any solution to this problem is going to have to satisfy this equality here. See, so does that make sense? Does the concept of informational dominance make sense? Okay, so another example is we could take the two black edges over here on the right, and then we notice that this sink edge here, whatever it's transmitting, is going to have to be a function of these two black edges, of the information transmitted across the two black edges. So we get another equality that has to be satisfied by any solution to this problem. And this is going to be the basis of showing that the rate is at most 2/3. Okay, so now I'm going to launch into the proof itself. I'm going to try and use pictures because I don't like messes of equations going across screens very quickly. Hopefully this will be a little bit more intuitive. So the idea is that when I draw this picture of the network here, and I've got two edges highlighted in black, what I'm representing with that is the joint entropy of those two edges. Okay, so here I have the two edges that I had in black on the previous slide. So I've got their joint entropy here. Over here on the right, I have those two edges plus the sink edge that they informationally dominate. So I know from informational dominance and the data processing inequality that the entropy of this set of edges is equal to the entropy of this set of edges. Okay. So now what I'll do is I'll add in the other equality that I had based on informational dominance. So I know that the entropy of this pair of edges is equal to the entropy of this triple of edges. Okay, and now you're going to have to go with pictures alone because I'm going to erase the equations. So what I'm going to do is I'm going to try and create a lower bound on this sum of entropies over here. And I'm going to do that by manipulating the entropies over here. So first off, yeah?
You can add like this only because the edges, on the right-hand side, the edges are all disjoint in the two cases? Or can you add no matter what?
So I had two, so if you look here, right, what I added together was I had this equality and I had this equality. And I just added them together. This is supposed to represent this joint entropy over here. This represents this joint entropy. So it's not like this picture represents together a joint entropy. Does that make sense? It's a sum of two joint entropies. Did that answer the question, or was there something?
I'm just wondering if on the left-hand side, was on the left-hand side, SG and F and SR and T are two separate sets of edges. The intersection set is not right. If that was not the case, can you still add like that?
Because I just have two. I just have two equalities here.
Yeah.
Right. So I'm just adding two equalities. Okay. Great. Okay, so what I'm going to do at this point is I'm going to start manipulating the joint entropies that I have on the right-hand side. Try and create a lower bound on some of the entropies on the left. So the first thing I do is I had sink edges in my joint entropies. So I had this sink edge and this joint entropy. I'm going to replace it by the corresponding source edge. And the reason is that in a network coding solution, the random variable transmitted over source edge is exactly the same as the random variable transmitted over sink edge. So I can swap these freely, without changing that joint entropy. And I do that in both of the joint entropies. Now the next thing is I'm going to try and create a lower bound on the sum of those two terms on the right. And I'm going to do that using the fact that entropy is a submodular set function. What that means is that the sum of the entropy of this set of edges plus the entropy of this set of edges is at least the sum of the entropy of the union of the set of edges plus its intersection. This is just the definition of submodularity. Okay, so now I know that this entropy plus this entropy is at least the entropy of this whole set plus this whole set. Where again, this is one joint entropy and this is one joint entropy. Okay, so the next thing is that I've managed, by taking the union of the two sets of edges, I've managed to create a pretty big set of edges over here. And what I'm going to do is I'm going to notice that the blue sink edge here is informationally dominated by this pair of edges. Again, just looking at the structure of the graph. What that means is that I can add the blue sink edge into that set without increasing the entropy of this term. And that means I haven't increased the entropy of this sum. Now I'm going to play the same trick I started off with. I'm going to replace the sink edge with its corresponding source edge. And that's what I get. And now I'm just going to remove the two middle black edges from the left-hand term. And obviously that doesn't increase the joint entropy of this term. So what I'm left with is two joint entropies, both of which only involve source edges. And we assumed at the beginning that the sources are independent. So that means I can break this up into the sum of the individual entropies of those sources. Okay? And so in other words, I can just count the number of times I have each source edge highlighted in black on this side. So I've got the green source edge twice, which is here. I've got the red source edge twice, which is here. And I've got the blue source edge once, which is here. And now what I'm going to do is I'm going to notice that I've managed to create a lower bound on the sum of those two entropies over there with this term over here on the right. And I'm going to erase this whole derivation and start working with the terms on the left. Okay. So those are the two original edge sets that I started with. And what I want to do is I'm going to break them up so that they're no longer joint entropies. So what I'll do is I'll break this up into the sum of the entropy of the two individual edges. And I can do that again because entropy is a submodular set function. So that means if I replace this by the sum of the entropies of the individual edges, I'm only increasing the left-hand side of this equation. So that's what I'll do first. And then I'll do a similar thing for the second term. And now what you notice is now I've got a set here, which is just the entropy of the red edge, and a set here, which is supposed to represent the entropy of this green source edge. I know exactly what those are, so I can put them in. And now what I'm going to do is I'm just going to cancel these two entropies from both sides. Okay, so I've done a lot of little manipulations, but the end result is that I have the sum of the entropy of this edge plus this edge has to be at least the entropy of the sum of the three sources. This is where our rate 2/3 comes from. Okay, so formally what we do is we use the fact that we assume the capacity of each of these edges was 1 and that their entropies were at most the capacity of the edge. And we also use the fact that each of the sources is transmitting at some rate r. This tells us that the rate has to be at most 2/3. Okay, so one thing this proof showed was it showed meagerness was not a tight bound. But more importantly, it was essentially a set of techniques that I can use for any problem to upper bound the rate. So let's try and generalize what we were doing. So essentially, I combined facts about entropy, for example, the fact that entropy is a submodular set function, with constraints based on the structure of the graph. And those I was referring to as informational dominance constraints. Now I can generalize these to get a set of linear constraints on a network coding solution for any problem. It results in, a large, what I mean by that is exponentially larger than the size of the graph, linear program. But it also has a fact that its optimal value is an upper bound on the capacity of the graph. Okay, so I want to talk about these constraints a little bit more. There's essentially two types of constraints. The first are information theoretic constraints. They just have to do with properties of information. They have nothing to do with the structure of the graph. So the ones that we were using were the fact that entropy is a submodular, non-negative, and non-decreasing set function. We also need to use the fact that I'm assuming the sources are independent, and therefore the joint entropy of a pair of sources is equal to the sum of their individual entropies. We're also using the fact that sources are assumed to transmit at least at rate r, so we get inequalities of this form in our linear program. And finally, the random variable transmitted on a source edge is the same as the random variable transmitted on the corresponding sink edge, which means that we get a bunch of equalities like this for any set of edges u. Now, the other types of constraints that we're using are constraints based on the structure of the graph. So there are two types of these as well. Probably the most obvious ones are the fact that I'm not allowing you to exceed the capacity of an edge. So that places a bunch of constraints like this in the linear program. The more important one in my mind is this informational dominance constraint. So I have a functional definition here which says that if the information transmitted on a set of edges A determines the information transmitted on a set of edges B, then A informationally dominates B. When this happens, the edges in A essentially are a bottleneck. Okay? And the reason is because I know from the data processing inequality that the entropy of the edges in A is equal to the entropy of the edges in A union B. That implies that the capacity of the edges in A are an upper bound on the entropy of not only the information transmitted across edges in A, but also the information transmitted across edges in B. So as I said, this is a functional definition that I've given you here. But it's essentially where the structure of the graph starts entering the problem. It's a really important condition, and I'm guessing some of you are probably starting to wonder, can you tell when a set of edges A informationally dominates another set B? You know, I sort of was hand-waving and saying, just look at the structure of the graph. It's obvious. So the natural question is the question A dominates B a decidable question? And it turns out, yes, it is. In fact, we've developed a polynomial time algorithm for deciding that question. And this algorithm is based on a structural characterization of informational dominance as opposed to the functional one that I just gave you. So the structural characterization is pretty involved. But I can give you two examples of structural conditions that imply informational dominance. And these are fairly simple, but you can use them to prove interesting theorems. So the first one is that if I have a set of nodes V, then the information coming into those nodes has to determine the information leaving it. In other words, what's leaving a set of nodes is a function of what comes into them. This implies that the in edges to a set of nodes V informationally dominates all the edges adjacent to V. So that probably should seem, yeah.
You said polynomial. How bad is a polynomial?
It's like quadratic in the size of the graph. It's not too bad. You have to just figure out some subgraphs and look for some connectivity constraints. Yeah. Okay, so the second condition here is the one that actually makes things a little bit more complicated. But let me just give you an example. So a source edge and a sink edge for a commodity are informationally dominated by a set of edges A if, when you remove A from the graph, the source edge and sink edge are in different weakly connected components. Okay? So it turns out that, in fact, if you think back to the first example I gave you in that green edge, if Si and Ti are in the same weakly connected component, there are times in which you can still get information from Si to Ti without ever changing the information that's transmitted across an edge A. Anyway, so these rules, yep.
Just remind me what the weakly component is.
So a weakly connected component means if you think about a directed graph and you just take paths reachability from every node to every other node, you put every node in the same set if it's reachable from some node. So in other words, think of it as undirecting every edge in the graph. Is there a path? That's probably the easiest way. Okay. Okay, so now what I'm going to do is I'm just going to use these simpler conditions which imply informational dominance. I'll use them to prove an interesting theorem. And let me just reassure you that this isn't going to go on too much longer. So this is where we are in the talk. I've already showed you a model for information flow in graphs. We've considered a cut-based condition that turned out to be loose, but it motivated a general outer bound. And it also motivated these techniques. And now what I'm going to do is I'm going to use this outer bound and those techniques to verify the Lee conjecture for a subclass of graphs. OK, so let's just recall what the Lee conjecture is. It says that in an undirected graph, the maximum network coding rate is equal to the maximum multi-commodity flow rate. This is saying that if I have a bunch of point-to-point connections in an undirected network, then I really shouldn't be doing any network coding. I might as well just be doing regular multi-commodity flow. So it turns out that the interesting cases for this conjecture occur when the maximum multi-commodity flow is strictly less than the sparsity. And the reason is, in undirected graphs, sparsity actually is an upper bound on the information flow rate. So what that means is that, if there's a gap between the rate that the multi-commodity flow can achieve and the sparsity bound, then it's possible that the information flow rate could be somewhere in between those two bounds. But in the case where maximum multi-commodity flow actually achieves sparsity, there's no room for information flows to eke out extra rate in undirected graphs. OK, so we're going to use our outer bound to verify this for an interesting for a class of graphs for which there's a gap between the sparsity and the maximum multi-commodity flow. And I'm going to demonstrate the proof, again, using a small example. OK, so I've drawn a semi-undirected network at the moment. Let me explain what I mean by it. So the undirected edges in this graph represent the physical undirected network. But I'm still going to use directed edges as an analysis tool to represent sources and sinks. And for this example, there are 4 commodities. And each commodity has demand 1. The capacity of every edge is 1. And it's not too hard to see that the sparsity of this graph is 1. It's also not that hard to show that the maximum multi-commodity flow is only 3/4. What I'm going to prove to you is that the maximum network coding rate, or the maximum information flow, is also equal to 3/4. OK, so is everyone good at this point? OK. Again, it's going to be a proof by picture. So again, when I draw a picture of the graph with a couple of highlighted edges in black, I'm using that to represent the joint entropy of those edges. So what we're going to start with on the left is we're going to have 3 in edges to the top node. So that top node on the right, if you look at the in edges to it, well, those in edges have to informationally dominate all the edges adjacent to it. So what I've drawn on the right here is the joint entropy of all edges adjacent to that node. OK. Now I'm going to consider the middle node on the right as well. So if I take the 3 in edges to the middle node on the right-hand side of the graph, I know that those in edges informationally dominate all the adjacent edges. Sorry, I should be saying, when I'm taking a directed edge in this undirected graph, what I'm meaning is I'm meaning the information transmitted in that direction on the edge. OK, and finally, I'm going to add in a constraint, an informational dominance constraint that we get based on looking at the bottom node on the right here, and I take all in edges again, and I get all edges adjacent to that bottom node. And now I'm going to do the same thing I did before. I'm going to start replacing the sink edges with their corresponding source edges in each of these terms. So for instance, on the right-hand side, if you look at the left-hand term, I have the blue sink edge, and I'm going to replace that with its corresponding blue source edge. Okay, and I haven't changed the entropy of any of those terms because sources and sinks are sending the same random variables. OK, so now what I do is I use some modularity. So I'm going to do this 2 steps at a time. So first, I'm going to consider these 2 terms. And I know that the sum of those 2 terms has to be at least the sum of the entropy of the union of those 2 edge sets plus the intersection. So this is the union of these 2 edge sets, and this is their intersection here. OK, so I was able to lower bound the right using submodularity. I'll do it again, where I'm going to take, I've now got the union of what was, I guess, all 3 terms over here. And here I have the intersection of what was the union plus this term on the right. OK, so now, again, I've created this term, which is essentially the union of these 3 edge sets here. And it's got a lot of edges in it. And so if I look at this set of edges, here I've got all these black edges in this joint entropy term. And if I were to remove all those black edges, there's no longer a path in an undirected sense from the pink source edge to the pink sink edge. So by removing all of these black edges, the source and the sink for this commodity are in different weakly connected components.
How did you get the bottom edge?
Okay, yeah. So I was here, and I now use submodularity to put this into the union, and then I have the intersection over here. Okay, so at this point, what I know is that this big set of black edges also informationally dominates that source edge. So I can add that source edge into that term without increasing the joint entropy that I have of that set. And now I can remove all those black edges again without increasing the joint entropy. And what I'm left with is, again, a sum of entropies of sources, because I'm assuming that the sources are independent. So in other words, I have the pink edge once over here on the right, and I have all the other source edges twice. So is that clear? OK, so that gives us a lower bound on the sum of the entropies of the 3 edge sets that we started with, which are the terms up on the left. And again, I'm going to remove the derivation and just work with that inequality. OK, so here we have the sum of the 3 edge sets on the left. And on the right, I've got a sum of entropies of the source edges. And what I'm going to do is I'm going to use submodularity to break this up and basically pull out the source edge from this term. So I can replace this joint entropy with the entropy of the green source edge plus the 2 undirected edges. And that only increases the left-hand side of the equation. So I do that. I do the same thing for the middle term by pulling out the red source edge. And the same thing with the right-hand term by pulling out the blue source edge. OK, and now what I'm going to do is I have these source edges by themselves. So I know exactly that the entropy of this set, for example, is just the entropy of the blue source edge. So I can replace each of these terms with the entropies that I know that they have. And now I'm going to cancel the entropies of the green source edge, red source edge, and blue source edge from both sides of the equation. And I'm left with this lower bound. So essentially what this lower bound is saying is that if I take the 2 edges into the upper right-hand node, plus the entropy of the 2 edges into the middle node, plus the entropy of the 2 edges into the bottom node, that has to have at least as much capacity as the 4 sources, the entropy of the 4 sources in the graph. So essentially, the entropy of the edges of the information traveling from left to right in this graph has to be at least as much as the entropy of the 4 sources. An entirely analogous argument using the edges going from right to left proves the following lower bound. OK. So now what I'm going to do is I'm going to add these two together. This is a little bit tricky. But on the right-hand side, it's completely obvious what I'm doing, right? I'm just adding these 2 terms. On the left-hand side, though, I'm using the fact that I'm assuming that the entropy of the information traveling in both directions on an undirected edge is at most the capacity of that edge. So for instance, if you look at this edge, the undirected edge that's being represented by this directed edge, I have this direction once, and I have the opposite direction once up top. When I take those 2 together, I know that the sum of those entropies has to be at most the capacity of the edge of the graph. OK. So now we assume that the capacity of every edge was 1, and we assume that each source was transmitting at rate r. What that says is that the rate is at most 3/4 for this example. OK. So I've shown you a lot of little examples.
Maybe off subject, but Kamal Jain proved the same thing a few weeks ago in his seminar. Maybe it's the same proof, maybe it's not. You may want to compare notes.
It actually is exactly the same proof. So we independently came up with this. And in fact, we also independently came up with the same or similar general theorem, which is that the maximum network coding rate is equal to the maximum multi-commodity flow rate for graphs that are undirected and bipartite, have capacity 1 for every edge, demand 1 for all commodities, and the distance between each source sink pair is 2. As a corollary, both Kamal and our group proved that there can exist a gap between the sparsity of a graph and the capacity, even when you're considering information networks. OK. So I'm just going to wrap up here. So what I did was, the first thing I showed you was a general outer bound that applies to any graph And this basically expands the result from Song-Yung and Tsai, which only applied to directed acyclic graphs, and now we can create an outer bound for any graph, whether it's undirected or contains cycles. This outer bound is based on combining constraints that are derived from the graph structure with properties of information. And I think this is kind of a useful idea. I really feel like network coding sits in the space between combinatorial techniques and information theory. Now, the other thing that comes out of our bound is it highlights the importance of this informational dominance relationship, because informational dominance essentially shows you where the bottlenecks in the graph are. So in our paper, we also present a polynomial time algorithm for informational dominance. When I say our paper, I mean the one being submitted today. So I'll have it up on my website soon. And finally, as sort of a corollary of what we did, we're able to verify the Lee conjecture for this interesting class of graphs where there's a gap between the rate that multi-commodity flow can achieve and the sparsity of the graph. OK, so finally, there are a ton of open questions in this area, some of which I personally think are interesting, are the following. So I'm going to start with a very theoretical question, which is that the bound I gave you used essentially only the following facts about entropy. I said the entropy is submodular, non-negative, and non-decreasing. These are known as the Shannon-type information inequalities, and that's because they're due to Shannon from 1948. More recently, there's been a development of what are called non-Shannon-type information inequalities, which cannot be derived from the basic inequalities, or the Shannon-type information inequalities. So in other words, these non-Shannon-type information inequalities give us a stronger notion of exactly what entropy looks like. And it's not clear. Maybe we actually need to include these non-Shannon-type information inequalities in order to get a tight upper bound on capacity. The hope is that we don't, because people don't actually understand non-Shannon-type information inequalities very well at the moment. On the other hand, my guess would be that we actually do need to include them. The second thing is that this Lee conjecture is very interesting. And both Kamal Jain and that group and us, we've only proved it for a small class of graphs. And in fact, all we've shown is a constant gap between sparsity and the achievable rate. So what would be really interesting in my mind is either to prove that conjecture in general, or at the very least consider 3 regular expanders and try and extend the Leighton-Rao gap to the case of information networks. And finally, an area that I think a lot of people are interested in but not quite sure how to move forward on is actually creating algorithms to use the full capacity of information networks. So one hope we have is that by now putting out an outer bound or an upper bound on capacity, we at least have a target to shoot for with approximation algorithms. OK, and that's all I have.
I have one question. So when you design an algorithm to really deliver information from source to things, because all the graphs you show here are they're symmetric in some sense.
OK.
So is that symmetry and the operation which you used, the exclusive OR, essential? When you have the algorithm to send information.
So one thing is there has been work showing that sometimes you need slightly more general functions than the exclusive OR. But on the other hand, it does seem like that original example that I put up is kind of the basis of why network coding or information flow is different than fluid flow. So that example where you are using, essentially tree structures and you are doing exclusive OR, that seems to be at the heart of what's going on.
Is there any other calculation besides this exclusive OR considered?
Well, so far all the algorithms actually just use variations of that. Sometimes the field sizes seem to be larger, so you're doing, linear functions over a field. But it's essentially the same idea. On the other hand, I guess there's been recent work by Randy Dougherty, Ken Ziegler, I'm forgetting the third author at the moment, but where they derived some interesting results by looking at some graphs or some network coding problems that are actually derived from matroids. And there they're showing some very interesting things that possibly we need to do more general things than just linear functions. Okay. Well, thank you.